Good day, students. On this clip, we're going to be going over two examples on right triangle trigonometry with a given point and an angle in standard position. So let's go ahead and write down the instruction for the examples. So we are to find the exact value of all six trig functions for the given point with the angle subtended in standard position. Okay. All right. So number one, we have the point 5 and -12. All right. So we want to find all six trig functions for this given point with the angle in standard position. So to find the angle in standard position, the first thing we're going to do is graph this point and find out where theta is. All right. So let's create our coordinate system. This is 5 to the right, -12 down is going to be in quadrant 4. So we're going to make quadrant 4 as big as possible. Now this is not being drawn to scale, so it's just a sketch. The quadrantal assignment is most important. So we have, let's just call this 5. Doesn't really matter where I put it. Remember, this is your positive x, and the x is positive here, and this is your negative y. So we're going to be downstairs here for the -12. So let's call this -12. All right. So where is 5, -12? It's this point where those two lines meet, intersection. So this is how you draw your angle. You draw your angle straight from the point to the origin. Okay. Now, since the angle is in standard position, theta is going to be a reference angle. Okay, so how do we draw the reference angle? We always draw from the terminal side to the nearest x. So this is going to be theta right here. Okay, so this tells me clearly that my triangle is going to be sitting right on the x-axis from the fourth quadrant. All right, so there goes my right triangle. So with this information, I can find out the length of the sides of my triangle. So I have I can call, so this is 5, this is positive 5 right here, and this side right here is the measure of this side, which is -12. Now since this is the angle, the side opposite that theta, the reference angle, is my opposite, and this side right here is my adjacent, and the side opposite the right angle, the 90-degree angle, is your hypotenuse. All right, now we can clearly see that in this triangle we have our A, O, but we're missing H. So how do we find H? We use right triangle trig. The Pythagorean theorem. The trig version of that, which is a squared plus o squared equals h squared. This is the same thing as a squared plus b squared equals c squared, the hypotenuse and the two legs. Substituting the measures in, we have 5 squared plus -12 squared equals h squared. All right. Now, simplifying further, we're gonna have 25 plus 144 equals h squared. When we add these two, we have 169 equals h squared. Now to get h by itself, we'll take the square root of both sides, and then we'll have h equals 13. All right, so that's what our hypotenuse. Our hypotenuse is 13. Now to finish this problem off, we're just going to use SOHCAHTOA and its reciprocal to figure out all six trig ratios. So we have SOHCAHTOA. So tells me that sine theta is opposite of a hypotenuse. So that's going to be -12 over 13. Its reciprocal is cosecant cosecant theta is negative 13 over 12. Next thing we have is cosine. Cosine theta from ka, we know that it's adjacent over hypotenuse, so it's going to be 5 over 13. It's reciprocal secant. Secant theta is the reciprocal of this, which is hypotenuse over adjacent. The tangent of theta is TOA, opposite of adjacent, so the opposite is negative 12 and the adjacent is 5. The reciprocal of tan, which is cotangent theta, is negative 5 over 12, just by reciprocating tan. Alright, so there goes all your 6 trig ratios for 5 and negative 12 and theta in standard position. Alright, let's take a look at question number 2. Same instructions. So for number 2, we have the coordinates 4 and 2 root 3. Okay? Alright, let's try this one out. So first thing I'm going to do is make a sketch of the situation. So where's the point? 4 and 2 root 3, they're both positive, so it's going to be in quadrant 1. We know that this is a positive x, my positive x, and this is my positive y. Okay? I'm sorry, this is y, positive y, and this is x. Alright, so let's graph the point. My x, let's just call this part right here 4. And then my y, this part right here is 2 root 3. It's not drawn to scale. So the point 4 comma 2 root 3 is going to be this point right here. And then the terminal side is the point that connects the origin to the point. Now theta is in standard position. Theta is going to be a reference angle, which is the angle between the terminal side and the closest x. This is the closest x right here. So this angle right here is going to be theta. Alright? So that clearly shows me that the triangle in standard position is going to be sitting right on the x-axis in quadrant 1. Now let's use our coordinates to label the sides. This side right here is congruent to this side. So this side length right here, which is our opposite, is going to be 2 root 3. This side right here has a length of 4, so our adjacent is going to be 4 units long. This is 90-degree angle. The side opposite the 90 degrees is the hypotenuse. And we do not know what the hypotenuse is. In order to find all 6 trig ratios, we need to find the hypotenuse, okay? So to find the hypotenuse, we're going to use the trig version of the Pythagorean theorem. A squared plus O squared equals H squared. Okay? Alright, when we substitute the values, we're going to have 4 squared plus 2 root 3 squared equals H squared. Okay? So 4 squared is 16. Now if we want to square 2 root 3, using the product property of exponents, we have to distribute this square to the 2 and to the root 3. If we make that distribution, we're going to have to square 2, which yields 4. And when you square root 3, you get 3. Okay? And that equals H squared. So we have 16 plus 12 equals H squared. 16 plus 12 is 28 equals H squared. So to get H by itself, we're going to have to take the square root of both sides. So root this and root this. That tells me that H is the square root of 28. Now can root 28 be simplified? Let's see. Let's pull it to the side and break it down. See any factors that repeat, then we can take the square root of that number. Alright, so we'll take out 2 since it's even. 2 times 14. You can take out another 2 since it's even. 2 times 7. And since these two 2's repeat, that's 4. So the square root of 4 is 2. So these two 2's come out as a 2, or a square root of 4, which is 2. So root 28 can be simplified into 2 root 7. Alright, so there goes your value for H. Okay, so H is going to be 2 root 7. Now that we have our hypotenuse, we can now go ahead and find the value of all six trig ratios, all right? So let's put the measure of h right there, 2 root 7, and let's generate our six trig ratios using SOHCAHTOA. SOHCAHTOA and its reciprocal, okay? All right, so starting with sine theta is going to be opposite of a hypotenuse. Our opposite is 2 root 3. Our hypotenuse is 2 root 7. Okay? We can divide out by 2's. These 2's divide out. And that leaves us with root 3 over root 7. Since 7, you cannot have a radical as a denominator, so we're going to rationalize the denominator with root 7 top and bottom. We'll multiply out, we're going to have root 21 over root 7 times 7 is root 49, which is 7. Okay? Alright, moving along to the reciprocal, which is cosecant. Cosecant theta is going to be the reciprocal of sine. So we just reciprocate. Let's just reciprocate this. We're going to have root 7 over root 3. Okay? You can put the 2's there, but the 2's cancel out. If I put the 2's here, they cancel out, so I can just reciprocate this piece right here. Alright? So now we have to rationalize the denominator. So we'll multiply by root 3 this time, top and bottom, since you have square root of 3 in the denominator. And then when you multiply it out, you're going to have root 21 over root 3 times root 3 is root 9, which is 3. Now moving along to cosine. From Chi, we know cosine theta is adjacent of a hypotenuse. Our adjacent is 4, and our hypotenuse is 2 root 7. Now 2 can go into itself on 4, so let's divide by 2 top and bottom. So 2 goes here 1, and 2 goes here twice. So it's going to become 2 over root 7. Now to rationalize the denominator, we'll multiply by root 7 top and bottom. Okay? Alright, so we'll multiply by root 7 top and bottom. And that gives us 2 root 7 in the numerator, and then root 7 times root 7 is, let's write that again, 2 root 7. Root 7 times root 7 in the denominator is root 49, which is just 7. Alright, so there goes cosine theta. Now for its reciprocal secant theta, we're going to have, we just reciprocate 4 over 2 root 7, so we have 2 root 7 over 4. Now to get rid of the, oh actually, all we can do here is basically divide by 2 top and bottom. So 2 goes here 1, and 2 goes here 2. So this simplifies into root 7 over 2. 7 over 2. Alright, now tan from TOA is opposite of adjacent. If we look at our triangle, the opposite is 2 root 3, adjacent is 4. So tan is going to be 2 root 3 divided by 4. Divide the numerator and the denominator by 2 since it's common. 2 goes here 1, 2 goes here 2. So that gives us root 3 over 2. Okay? Last but not the least is the reciprocal of tan, which is cotangent theta. We're just going to reciprocate 4 over 2 root 3. So we're going to have, it's going to be 4 divided by 2 root 3. Now we can divide by 2, top and bottom. 2 goes here 1, 2 goes here twice. And that gives us 2 over root 3. And then to get rid of the square root in the denominator, we'll multiply by root 3 top and bottom. So we have root 3 and then root 3. And that yields 2 root 3 over 3. Okay? Alright, so there goes our 6 trig ratios. Let's organize them in a nice list. We have sine theta equals root 14 over 7. Cosecant theta equals root 21 over 3. Cosine theta equals 2 root 7 over 7. Secant theta equals root 7 over 2. And we have tan theta equals root 3 over 2. And cotangent theta equals 2 root 3 over 3. Alright, so there goes our six trig ratios. So thanks so much for taking the time to watch this presentation. You can feel free to subscribe by clicking up here. Please post a comment to tell me what you think about this presentation. More clips can be found on mathchef.com. Thanks again and have a wonderful day.